Electricity. It's this invisible force that powers pretty much our entire world, right? From the phone you're holding to the lights in your room, we use it every single second. But have you ever just stopped and wondered, what is it really? So today, let's unplug the jargon and get right to the core of how it all actually works. I mean, think about it. You flip a switch and boom, a room is flooded with light, almost instantly. It feels like magic, doesn't it? But it's not. It's just science. So what's the secret? What is actually going on inside those wires to make things glow and heat up and just come to life? Well, let's find out. To answer that question, we have to start with the flow itself. We need to figure out what's actually moving through the wires. And that moving stuff is what scientists call electric current. Okay, the easiest way to get your head around this is with a simple analogy. Just picture a water pipe. The amount of water that's flowing past any given point every second, that's its current. Well, electric current is basically the same idea, but instead of water molecules, we're talking about a flow of tiny, tiny charged particles. So officially, electric current is the rate of flow of electric charge. Now, in a typical wire, that charge comes from a stream of electrons. We measure this flow in a unit called amps, or you'll usually just hear amps. And get this. Just one single amp is equal to about 6 quintillion electrons flowing past a single point every single second. It's a massive, invisible river flowing through our walls. So, okay, we have a flow, right? A current of electrons. But what makes them move in the first place? Electrons don't just decide to go for a jog down a wire for fun. They need a push. And that push is what we call voltage. Let's go right back to our water pipe. Water won't flow through a perfectly level pipe, right? It needs a pressure difference. Maybe you have a pump or a water tower creating pressure at one end. Well, voltage is the electrical version of that water pressure. It's the force that gets those electrons moving along the circuit. Now, the more formal term for this electrical pressure is potential difference. A battery, for instance, uses a chemical reaction to create this difference. It's kind of like it creates an uphill and a downhill for the charges. The voltage, which we measure in volts, tells you exactly how much energy or push each one of those charges gets to make its journey. All right, so we've got a flow, the current, and we've got a push, the voltage. But the universe always has to have some kind of friction, doesn't it? In electricity, that friction is called resistance, and it's the third and final piece of our fundamental puzzle. Back to our trusty water pipe one more time. If the pipe gets narrower, or if it's kind of clogged up, it's obviously going to be harder for water to flow, even with the same amount of pressure pushing it. Resistance in a wire is the exact same concept. It's anything in the material that gets in the way and resists that flow of electrons. Every material has this property. Good conductors, like copper, they have very, very low resistance. They're like wide, clean pipes. On the other hand, insulators, like rubber, have incredibly high resistance. They basically block the flow completely. We measure this property in a unit called the ohm, and it's represented by that Greek letter, omega. And this brings us to the man who connected all three of these ideas together, George Simon Ohm. Way back in 1827, he discovered this beautifully simple relationship between the push, the flow, and the friction in a circuit. He figured out that if you increase the push, the voltage, you get more flow, more current, and it's all perfectly proportional. And here it is, Ohm's law. Voltage equals current times resistance. You'll usually see it as V equals I times R. This wonderfully simple formula is the absolute foundation of all circuit analysis. If you know any two of these values, you can always figure out the third. It's the elegant, predictable rule that makes all of this work. So now that we have our three key ingredients, voltage, current, and resistance, let's see how they actually work in the real world. Turns out we can connect things in a circuit in two basic ways. We can wire them in series, or we can wire them in parallel. You know those old-fashioned holiday lights? The ones where if one bulb goes out, the entire string just dies? So frustrating, right? Well, that's a series circuit. There's only one single path for the current, so if it's broken anywhere, the whole thing stops. Now, in a parallel circuit, the current splits up, and each bulb gets its own little path, so if one goes out, the others stay lit. And thank goodness this is how your house is wired. Now, the way you wire a circuit totally changes its total resistance. In series, it's really simple. You just add up the resistance of each part. The more things you add, the harder it is for the current to get through. But in parallel, something really interesting happens. The total resistance actually goes down. You can think of it like opening more checkout lanes at a grocery store. You're giving the current more paths to take, which makes the whole journey easier overall. So, we've got current flowing through these resistors. What happens to all that energy? It doesn't just disappear. Let's take a look at the real-world consequences, which often involve a bit of heat and, yep, your electricity bill. Remember how we said resistance is kind of like friction? Well, just like when you rub your hands together and they create warmth, pushing all those electrons through a resistor generates heat. This is called Joule's law of heating. Now, sometimes this heat is an unwanted side effect, like in your computer, but sometimes that heat is the entire point. And this effect is at work all around you. A toaster? That's basically just a special high-resistance wire that's designed to get incredibly hot. The same goes for an electric heater or an iron. Even an old incandescent light bulb works this way. It's just a tiny wire, the filament, being heated until it actually glows. The rate at which any device uses this electrical energy is what we call its power, and we measure it in watts. So a 100-watt light bulb is using energy faster than a 60-watt bulb. And this rate of energy consumption is exactly what the electric company is measuring and, well, what they bill you for. So let's connect this right to your wallet. Let's say you have a standard 400-watt refrigerator and it runs for about 8 hours a day. Over a whole month, that would cost you about 288 rupees to operate. Every single watt used over time, it all adds up. That is the direct link between the physics of electricity and your monthly bill. Okay, so we've covered the what, the why, and the how of electricity's flow. We get current, voltage, and resistance now. We've seen how they all work together in circuits to produce power. But, all of this depends on having a source of that electric push to start with. So that leaves us with one final and really fascinating question. How do we actually generate it? But that is a story for another time. Thanks for watching.